Plenty of time. At least a couple of years. That it would be nice.
Yeah, I guess so. I mean, I think it's going to be around for, like, I think it's a real thing that will be useful, but I think if you're reaching the end of where you can just do anything
And
add a little
get
machine
here
learning into
overnight.
it.
Exactly.
That's true. It was really, like, you know, like Roger Belko is like through some of that, they're like really, like, he's written a bunch of this, like, many body papers on this, and it's like a lot of that stuff. So, yeah, it's pretty interesting.
Yeah, our next speaker is Jin Zhongchen from Academia Sinica. He's going to talk about artificial neural network in statistical modeling of dynamical systems.
I'd like to thank the organizer for inviting me to present our recent work on this subject. And this is actually an ongoing research project, and it's in collaboration with Inguo, who's an academic in Academia Sinica, and it's also a distinguished professor at the National University. And this is our postdoc training. So first, I would like to talk a little bit about the ideas of the statistical modeling, and then show that the result of how this can be applied to different systems. And then I'll mention the bottleneck of this problem, and then also problems involved in applying these methods, and also how machine learning can help. And I'll show some examples of our efforts. So first, what is statistical modeling? So the idea is very simple. And in short, it can be summarized as if something that walks like a duck and quacks like a duck and looks like a duck, then it must be a duck. Okay, so basically, what the problem we're facing is that the approach we are adapting is a top-down approach. We start from the macroscopic behaviors of the system, the views of the system, and then it's completely data-driven, where we build from the observed data instead of trying to come up the microscopic mechanisms of the system and then build things up. Also, we're considering the collective behaviors and the collective phenomena instead of how like individual agents behave in these systems. Okay, and the reason that we need to we want to apply this statistical modeling is that due to this big data and then also this dynamic data, And because of the technology of measuring things in this dynamical system becomes more and more advanced, it is very easy that you can acquire the large volumes of these data, and it's becomes costly, very costly to analyzing them in details, and then try to dig out this useful information from these big volumes of data. And here you can see this typical recording, especially for the system we're interested in the neural systems. So these are electrodes, and you can see new pictures of these neurons growing on these electrodes, and you can measure their local field potential and try to infer that when these neurons may have spiked. And this is another example. This is an experiment published in Nature Neuroscience. It's showing a mouse right here, and it's running or walking on the styrofoam ball. It's like a track ball. And there are screens that showing a visual reality to the mouse. And then when the mouse walks, it's walking in an environment like this. It's like a virtual maze for the mouse. And then there's a microscope that is looking into the cortex of the mouse brain and try to measure whenever the neuron in the mouse brain fires, the calcium level will get higher, and there's a fluorescence. I don't know the details how they did this, but it will light up, and then you can see these pictures or videos of how these neurons light up in the mouse brain as the mouse is walking in these maze. Okay, so these are the recordings, images from the mouse brain, and you can identify the neurons in these pictures, and then you can see that how their intensity of calcium vary over time. Okay, and here is some example from our collaborator in the China Medical University, and they're also doing something similar, but it's not in a virtual reality, but in a real chamber for the mouse. And this is how it's behaving, and this is how the neurons are firing. The image can be blurry, so it needs to be intense, and then the data need to be extracted from this, and then you can compare it with how the mouse is behaving. Okay, and this is another example published in by Bialek and his co-workers in PNAS. It's basically studying like a flock of birds. And try to vectorize the flying direction of this bird. And also they're going to get the similar information like this orientation as a function of time for each bird. And then they can infer to how they interact using the statistical model I'm going to mention. Okay, so the idea is that if you have this time trace or dynamical information, you try to convert them into a binary system configuration, and then you can look at this like it's a spin glass model or like an icing model, whether it's two-dimensional or coupled. So you can match the properties of this magnetization for every spins, and also correlations between the spins. And this is a spin glass model energy. You can write it down, and basically you have two kinds of parameters to deal with. One is this H, like a local field parameter, and one is this Ij, which is coupling between degrees of freedoms. Okay, so with this model, you can also perform like simulations to produce this Mi and the Cij, the magnetization, the local magnetization, and also the correlation. And you can compare it with what you get from these experimental measurements. Okay, so this idea was the earlier pioneer, this William Bialek, and he had many papers published using this method or related to these methods. And the basic idea is that you take these data and you do abstraction or segmentation to make them binary states. And then you make them to spin gas models, and then you find these appropriate model parameter hi and the jij. They can reproduce your data and compare them to your observed the mi and the cij, and try to do an adjustment to this hi and jij so that it can give you better and better approximation. And then eventually, with this model, you can generate artificial data, and then you can compare them with the real data and see how they compare to each other. Okay, so how good is this mapping is? So in order to test this model, so this model, if you look at the interaction, it only involves like 2 spin interactions. There's no higher order interactions. So basically, it's saying that all the configuration showing up is due to the interaction between the 2 degrees of freedoms, arbitrary any pairs of degrees of freedom. There's no higher order like three spin interactions involved in this model. Okay, so basically, what the first thing that you can test is how good this assumption is that it's no surprise this model will be able to reproduce this 2-point correlation function. But you can also ask that how good this model will allow you to predict the 3-point correlation functions for the systems. And then from the comparison, you can see that it actually fits pretty well for many systems. So that means these systems, the 2-point interactions is enough to describe their behavior. And also they can ask this kind of questions that how well can one spin be predicted by the configurations of other spins in the system? So this is kind of related to the predictability of each spin, individual spin in the system. And they apply that to the mouse data when the mouse walking in the maze. They found that it matched pretty well with the experiment. So what you can see is the red line is the binary event they measure from the experiment. And then these lines, these black lines are the probability that this neuron should fire when you predict from the firing state of other neurons in the system. So it's quite well predicted. And there's actually some subtle difference. So there are actually 2 kinds of neurons they found in this system. One is that, look at this kind of neuron, its prediction is pretty accurate. But there's another kind of neuron, it's close, but not so accurately predicted by other spins of the system. And they actually are related to whether they are place cells or not place cells in this system. So I don't know many of you have heard of the place cells in like mouse brain or human brain. So there are certain cells that can relate to the they're fired up when the mouse reaches a certain position in space. And these cells, like GPS in the mouse brain, they tell the mouse where it is right now. And these have quite different behavior from other types of neurons in the mouse brain. And you can also perform information theoretical analysis by looking at the mutual information between the states of the neuron and the positions of the mouse. So they found that for place cells, these mutual information are pretty close to what's predicted from the firing of other neurons, while for the non-place cells, there are the deviations between the 2. So the information predicted from the firing of other neurons and the position information are quite different for non-place cells. Okay, so this is something useful for this kind of a system. Okay, so far this is a promising method, and it helps us to understand the behaviors of the system simply by looking at the data, the dynamical behavior they're generating, without knowing the microscopic details of how it works. But there's a big bottleneck of this process, namely how to find the correct the parameters, model parameters, hi and this jij. And then our proposal is to use the machine learning approaches to help us solve this problem. And there are many types of machine learnings that you have heard of it in previous talks on supervised learning and unsupervised learning. And for supervised learning, you are required to like data and also labels to train your neural network. Unsupervised learning basically try to cluster your samples without giving it the labels. Let the machine classify them all by itself. So typically to solve this problem, because this basically is a Boltzmann, so-called Boltzmann machine, and you want to find parameters that reproduce this sigma, the mean of the sigma I, so it's local minimization, and also the covariate, the mean, the the mean spin products, this correlation. What you can do is you can try to take a guess of this how this H and the Jij should be, and then you perform this Markov chain Monte Carlo to come up to calculate this MI and the Cij for the model. And if it's different from the experiment, you adjust your Hi and Jij accordingly following this. And then basically, these differences are actually the gradient in the log likelihood of how these two distributions are close to each other. So basically, when you take this shape, you're walking along the way the minimum gradient so that you can minimize the difference between the two distributions. And so, but the first thing you need to do is from the raw data, which is the 101 and the 0101 configurations data that you have measured. You need to first calculate an ensemble average to find this MI and this Cij. And then also from the model, you need to perform this MCMC simulation, and so that you can find the difference between the two and then tell you how to adjust your parameters. But what we think that we can probably do it much faster if we have a machine that can simply tell us what this Hi and the Jij means. What this Hi and Jij are when we give it the input, the MI and the Cij as input. So if we can do this, this is almost instantly. Like it can give us the answer. The problem is that how do you construct this machine and how do you train this machine? So this needs to be trained. And how do we train it? Basically, we don't have that many data to train it. Even from the experiment, we don't know what's the underlying Hi or Jij. But since this, if we know the Hi and Jij, we can calculate the MI and Cij using Monte Carlo simulations, the Markov chain Monte Carlo. So we can use random number generators to generate sets of the Hi and Jij. We can generate as many sets as we want. And then we can do these MCMC simulations to generate the sample. And we use these pairs to train our machine. And afterwards, we can feed the MI and Cij from the measured data to the machine, and so that you can produce the Hi and Jij. So that's the idea. And these are the sample distribution we use to generate this Hi and the Jij with single peak, and 2 peaks, and 3 peaks. Okay. And this is the first machine that we tried. So this is basically a multi-layer perceptron, and you have this you feed in this MI and this Cij, and you have each layers that's fully connected. And then output, you ask it to predict this Hi and Jij. And I think actually can work. If you train it, you can see the error for the training data is in orange and test set is in green. It can go down. This is 3 hidden layers, and when you have 4 hidden layers, you You can see there's some overtraining here. And this is how many samples that you use. So this is more you use more samples to train the machine, you use less samples to train it. But then this is very costly, so it's very converged very slowly. What you're seeing here is actually on log scales. So this is log time scale. So it's pretty slow, and it's growing exponentially with the number of weights and parameters, also with the number of layers. So our postdoc can come up with an idea. So, since the CNN is so popular nowadays, why don't we just use the CNN to do this job as a black box? But actually, it's not so intuitive because we don't have an image in this case, right? And CNN usually used to process image. It's doing a good job in image processing. But it just said that we have a covariance matrix. We can simply treat this like an image. Okay, so it's a 2D image. So we have, for example, the 64 neurons would be 64 by 64. And you can use a convolution kernel. You can have like many of them, like several of them, if you consider different features, and you scan it over, and you can have different CNN layers, and then at the end you use a perceptron to read out this prediction and ask it to predict this H or this J values from the input covariance matrix. And it turns out works to a degree. So you can see the error can go down as you train this machine. And at the end you can get, if the machine is well trained, and you can test it using like different HI and GIJ from the same distribution, they can actually fit pretty well with the with the truth. Okay, so this is surprising because the covariance matrix is not an image. There is no like translational inference in such a covariance matrix. But you do have like things like permutation inference. So that means if you change the indexes of the neurons, the problem should remain the same. But it's not an image. And so it works. That's surprising. But it doesn't work all the time because the training data set, you need to know what kind of HI and GIJ set that you need to use to train your machine, but you don't have that information from your experimental data. So you don't know that. So you can only guess. And then it also doesn't work quite well when you have an anti-ferromagnetic coupling or in some like low temperature or in gaseous state. But I think this is a very difficult situation that I don't think there's any ways of solving it now. But what you can still use is that we found that if you can because you don't know whether your training data set is good or not, you don't know whether it covers your case. What you can do is that if you have experimental data, then you can dynamically modify your training data set as you try to predict the HI and GIJ of the observed systems. And also for like when you're in the anti-ferromagnetic coupling case, maybe you can use the replica method in your MCMC. So there are possible solutions. Okay, so also if you use the predictions of the as the initial condition for the Boltzmann learning, it actually works better than when you use like a random initial configuration or like zero initial configuration for your Boltzmann learning. So there's still some use for these CNN predictions. And there are also hybrid approaches that we have attempted. So we start with lower quality calculations of this MCMC, and then move up. I mean, as you get closer to the answer, we move up, use a more higher longer MCMC rounds to calculate the more accurate the covariance matrices and the magnetization. And this is some results showing that how well it's working. It's not very impressive, but it does help a little bit. And this is final result if you use this initial condition. And at the end, you can use the Boltzmann learning to improve your data, and eventually you can get a quite well fit. Okay, so all these methods require an accurate local magnetization and also correlation. But what if you don't have this good configuration? I mean, for example, if you at like low temperatures, so this is no problem when you're in the high temperature phase. You can see this number of configurations. So this is on the log scale. Convert this value, the MI and the CIJ converge pretty quick. And then the critical temperature is also not so bad. But when you put at a low temperature, then you can see that even if you run like this is about a million steps, still can see quite big variations in this calculation for the M and the CIJ, MI and CIJ. So it will be better if we have a method that can calculate this without calculating these ensemble average first. So that, what we also tried is using a generative learning. So the idea is to use a Boltzmann machine, and specifically we consider a restricted Boltzmann machine because we know there's a quite efficient training method for restricted Boltzmann machine. That is a contrastive divergence method. And so what we need to do is to turn our Boltzmann machine into a restricted one by replacing all these couplings, this Jij, into hidden layers, hidden nodes in the layers. So this is the new Hamiltonian or new energy for the, we call it the pair restricted Boltzmann machine, pair RBM, and it involves these visible nodes. So these are original binary states for the one we measured in the experiment, and this is the hidden nodes corresponding to the links between the visible nodes, and this is the couplings. And you can use this contrastive divergence to train your restricted Boltzmann machine, and you're supposed to, I mean, if this method works, then you're supposed to get good results. But it also takes time. And then actually, after this calculation, the problem can be mapped back to the original Jij. There's an exact mapping that you can calculate analytically. So this is the way for the pair RBM, and you can calculate back what the J should be from these weights, and what the H should be. So these are exact forms. But okay, but so this other line for these pairables restricted pair RBM is that this machine can train on row configuration instead of these ensemble averages, and their parameters can be mapped back to the spin gas exactly. And there's some results also 4,000 samples, so you can train it with different number of samples. But then we found there's some problems with convergence in some situation where you can get stuck in the zero for a long time unless you use a very huge number of samples to train this network. Okay, okay. So also this is showing different when you have in a different temperature region. Basically, it's actually more robust to different temperatures. And besides doing these methods, we also try to improve on this Boltzmann learning by considering adaptive learning rates. And as you can see, where you can see these two lines are when you use fixed rate, and the other two, the red and greens, are using adaptive rates, where you initialize with different values, and then initially they're not as fast, but then at the end you can converge faster than the fixed rate ones. But there's also some problems. For example, in this case, specific case, although this convergence in the H and J, because we're testing it on configurations that we generate, so we know the ground truth. But if you look at the M and C, there's kind of a jump here, and it doesn't seem to converge. The MCs are still quite different from what you want at the end of this iterative process. And this can be helped if you use a more prudent adaptation. So the way we adapt the rate is that if we see the error becomes smaller, then we'll try to increase the rate so they can move faster. And if the error becomes bigger, then we try to reduce the rate so it moves slower. But if you do it more prudently, if you do it too quickly, then you kind of oscillate a lot, and then the error will remain at the same value without convergence. But if you do it more prudently, then for example, you see the error going up for several steps before you do the adjustment, or going down for several steps before you do the adjustment, improve this method and make it more robust. Okay. So beside that, we also consider like generation of these training samples iteratively. That is, when we have a raw data in order to we want to find the correct H and J, we use our machine to make a prediction. So the predictions, which will be this H and J, we have this M and C from experiment. It predicts H and J. We can use the MCMC to calculate the corresponding to MI and CIJ. And then when these two does not agree, we can use the MC results pair here as a training sample to keep train our machine. Okay, so if we do this, we can generate a dynamic training data set as we go. But the problem is that somehow this is a good idea, but the problem is that it doesn't seem to converge very well. So at the end, what we currently adopting is a combination of this CNN and also Boltzmann learning. So the idea is that we have the data, MI and CIJ from the data. We ask the machine to do the prediction, and at the same time, we also do the Boltzmann learning. So using Boltzmann learning, we have a model, H and J, to using MCMC, we'll calculate this M and C and compare, and then if it doesn't agree, we'll adjust this H and J, HI and JIJ. And this part is the Boltzmann learning, and this part is this CNN or this machine prediction black box, where we also ask the machine to make a prediction, and then we have MCMC simulation to calculate the MI and CIJ to check whether it's good or not. And all these calculations from this MCMC will be used as a training data set to train this machine on the fly. So all these will be done concurrently. And whenever this results from the machine is better than the Boltzmann learning, then this will be used to, this HI and JIJ will be used to replace this model HI and JIJ. Okay, so these are the results for this combining this Boltzmann learning and the CNN, using the CNN as our machine. So in this case, we're using CNN, a fresh CNN, so it's not trained in any way before we start the process. And as you can see, this Boltzmann learning scheduling can converge pretty well. So the CNN doesn't help at all. But sometimes it does help because the prediction happened to be better than the Boltzmann learning. So we replace it, and so that you can see this, the blue ones can go down earlier than this one without using the CNN. And this one also doesn't help, but this one does. And this one actually made it worse. So without CNN, you go down earlier than when you do it with CNN. And these two are not so conclusive. But this is the case with the fresh CNN machine, the fresh machine you train on the fly. And here is the case when you reuse the last CNN, so we do this one, and then our CNN, we don't start from fresh for the second, we use the previous CNN to keep training it. As you can see here, the results are much better. We have a 1, 2, 3, 4, like 5 out of the 8 cases that make an improvement to this convergence, to make it converge faster. So summarize. So we use this statistical modeling to characterize functional structures of systems. We simplify the model. In this case, we use this spin glass model. And the bottleneck of this process, of this statistical modeling process, is finding the model parameters that can reproduce the statistics of observed dynamics. And then using the Boltzmann learning, which is the conventional approach, it can be slowed because actually the landscape can be rugged in this cost function. And the simple CNN works surprisingly well when it's trained with considered distribution, but the accuracy can be limited. And then we can initialize Boltzmann learning with the CNN predictions and use adaptive algorithm, and we can also use CNN that, and also Boltzmann learning can be helped even when we use a naive, that is a fresh CNN that is trained on the fly. That can help us better convergence. And what's our ongoing project? And so what's the next thing we'll consider? So we analyzing the recovery structure in terms of complex network. We can also apply this method to internal states of this artificial neural network to understand how this block the box. Because the internal states, like the hidden layers, they also can show up in like you can consider them as configurations where you can consider each node having in a state 0 or 1. So you can use a same state modeling approach for this internal state. And then also we'll consider, because in this case, in the current study, we only consider the distribution of configurations. So there is no dynamics. Actually, there's no dynamics involved. So we can consider the temporal correlations for dynamics in the future. And also we'll take advantage of the permutation symmetry. Because the index of these neurons is assigned arbitrarily. We do not have the translational invariance like for CNN in the image processing, but we do have the permutation invariance for the indexes of the neurons. And this should be taken advantage of in the future. But we'll also apply this important statistical concept to characterize the result we get from this experimental measured dynamical data on neural systems from the brains of flies and mice. Okay, so I'll stop here. Thank you for your attention.
There is a special reason why you want to use the Boltzmann learning, because the machine learning community stopped using the energy-based learning because of just the rapid landscape.
The idea is to map it to a simple model, and the simplest one is this spin glass model. And we haven't exactly have the same structure as this the Boltzmann learning that has been used.
But you try like a recurrent neural network, you don't want to do the dynamics, maybe that's.
So we haven't tried because these are distributions, right? So they have no like order. We don't consider the order of the states. But in the future, if we consider this as a dynamical signal, so that one state leads to another, then time sequence information is important. And then in that case, probably it's necessary to have a recurrent network.
So, each one mentioned how big the system size that you can train?
Like up to 100.
Like 100?
Actually, yeah, there's 100 spin, and the coupling will be 100 by 100. Yeah. further questions?
If no further questions, let's take the speaker.
Thank you.
Our next speaker is Charlie Wong. Let's Kawai's talk will be very broad, deep learning in the large and small universes. So about stellar objects, application in astronomy and brain.
Okay, so good afternoon, everyone. So it's the next talk. I think you must be very excited because you're going to leave to see your families and relatives very soon. Okay, and so I hope that I could finish it on time, and so we can also have some interesting discussion. And the topic of this talk is very different from what you learned before because it's not very directly related to physics. I believe it is also very interesting, and I hope also you can find it inspired from this kind of approach. So basically, I will talk about two of my recent research. So first of all, let me introduce my current research related to artificial intelligence, including at least 4 subjects. Okay, the first one is something I'm going to talk later about, search the young stellar objects, which is related to astronomy. And I will explain it later. The second subject is related to neuroscience, which is to identify the neuron polarity of Drosophila brain, which is a kind of light. Okay. And the third project is related to natural language processing, which is to predict the current judgment. Okay, so party A and party B, and they say something, right? And they judge which one should win. Okay, so that's something collaborate with my colleagues in the Institute of Science and Law. Okay, and finally, of course, I still also have some works related to physics, but it just starts recently, so we haven't been able to say too much at this moment. But just let you know that I'm also doing something related to physics. Okay. So in this talk, I talk about these 2 subjects. One is related to astronomy, and one is related to brain sciences. So I will talk to you more details later. Okay, about the astronomy science, I believe that many of you have heard the application of neural networks to astronomy. But for us, the problem is following. But we see that there are many stars in the skies, right? There's so many billions and billions. Okay, but we are interested in a certain type of objects, which they call young stellar objects, which is basically a newborn star. Okay, it is very different from regular star in the sense is that it's still developing. So there are many other materials outside. Okay, so the spectrum or many other physics are different. For example, what's the effect of magnetic field, okay, and how the star is formed during this process. What's the most important physics behind it? So it is important. But the problem is the following: most of this kind of stars are not young stars. Or how did you find young stars, right? Because there are so many stars. So the first, less than 1% or 0.1% are really young stars. So it is the first question is where it is, right? So the situation is more difficult. Okay, it's actually even more difficult. So here, let's see. Basically, there will be at least 3 or somebody say 4 stages for star to form. Okay, initially, okay, there are some dust around and they collapse due to the gravity, as you should know, and then form a planetary disk. And along this disk, there are some planets around. Okay, but of course, this happens if we look at it in detail, observe for a long time. But most of the time, they are just a point in our telescope, right? We don't see the structures. Okay, so therefore, how can we distinguish them? One of the easiest ways to start to distinguish them from the spectrum. So here, the black body spectrum looks like this. Here's the wavelengths and the intensity. Right? But because there are many dust around, these dust are usually of lower temperature. So you are expecting to have additional infrared distributions. So it's different from black body radiation. And when it becomes more and more mature, so this additional structure becomes less and less. Okay, you can imagine, okay, probably that's the way we can distinguish young stars from mature stars. But the situation is not so simple because we also have this, like this galaxy, billions of stars. Okay, it's totally different from a single star. However, these galaxies are even farther away, right? So for telescope, unless you pay a lot of attention to have a better resolution, there's no way to distinguish these two. Okay, for galaxies, we also have a very bright center and also dust around, right? So you imagine that from the shape looks very similar, although this one, of course, is much larger. Okay, but in telescope, both of them are almost like a point source. Okay, because they can be very far away unless you pay a lot of attention to maximize your observation time. So therefore, the problem is that how can we distinguish? Okay, so first of all, let me show the data we have. So basically, we collect the data from several regions in the space, and for these red regions, that's where people believe that there's no young star because that's the star we can see is in the galaxy, our galaxy. For stars outside our galaxy, this is not observable because we just observe galaxies, not stars. So anyway, so we also choose data from different bands, different wavelengths, and that's a filter means that different projects or different observatory can measure different wavelengths. So basically, we have 8 wavelengths. Okay, so what result we have? Let's show you the raw data we have. Okay, this is the regular stars. That's what I said, so-called black body radiation. The wavelengths is the intensity. Okay, that should be usual, right? Here we have normalized it, so that because some stars are darker, but when we normalize it, it looks like a black body radiation. And here that's an arrow bar. And you can see that the arrow bar is larger in longer wavelengths because it takes a longer time, right, to take the data and whatever. So usually people do not believe the results in longer wavelengths because the fluctuation is larger. Okay. But what happened to galaxy? You can see that it can be anything. So it's a very different. You can see galaxy is very different from stars. Okay, fine. But why I saw this as future? Okay. So it also different from regular stars, but somehow looks like galaxy, but you don't know what's the structure. Right? So that's what confused people. Because we will not say they are the same, but well, most of them are like a mess. Okay, not as the standard as the regular stars. Okay, so our question is AI can help us. Okay, is it possible for machine learning can do better? Okay, let me show you the data further. So here is the spectrum in different bands, so in different wavelengths. And but the horizontal line is the flux, okay, the intensity. The vertical line is the arrow, because when you measure it, you can measure the average and also the arrow, right? So this distribution has there are 3 colors. 3 colors mean that the red one is star, green galaxy, blue one is YSO. You can see that in short wavelengths, they are always almost on each other, on top of each other. It's very hard to distinguish. But gradually, in longer distance, longer wavelengths, it seems that a little bit separable. But it is still very difficult to separate them, right? Because most of them are still up together. And also, you can see the arrow somehow proportional to flux because that's a statistical error. Okay, and there are two branches because the data are obtained from two kinds of projects. In one project, maybe take a longer time to measure, so the average error becomes lower. In another project, even looking at the same stars, but because they take a shorter time, so the error bar becomes larger. So anyway, that's the data we have. So we have actually more than 200,000 data right here. Okay, of course we can get more, but that's just the typical result we can have. So how do we do this? So first of all, we set some feature, which means the intensity of 8 wavelengths and their error bars. That's totally 16 numbers. Okay, and we put into the CNN with layer structures and all of you know it. But the problem is following: how do we know the answer? The answer actually was provided by previous theory. When we say theory, it's not a simple theory; it's combined many different assumptions, and so human beings make well. The reason I know it is because one of the authors is Professor Lai in our Institute of Astronomy. She was also one of the participants of this project. So she knows that how this data was collected. They also have to do identifications by human beings during the process. So it's not purely theory, but part of also involve human decision. Anyway, they have classified some stars. So that's some stars we assume it is correct, but actually it may not be correct. Okay, it's just based on known theory already. So that's how we start our supervised training. Okay, so in this data, actually we do much more than what I said. Originally, we can say we can use only 8 bands, so-called SED, spectrum of energy distribution, to do the classification. But we can also do further. We can include errors, and we can use normalized results. The reason is that for galaxies usually is very far away, so the intensity usually is weaker. But stars usually within our galaxy, so the intensity is usually larger. So in some sense, you may distinguish stars from galaxies by their overall intensity. But that's unfair, right? Because we are interested in their structure. This structure should not be changed due to their distance. So we are asking if it is possible for us to distinguish galaxy from YSO from the normalized intensity, not just from the overall intensity. Okay. Then finally, we also use so-called reduced SED, means that maybe we can get this information by only a few important features. What's the most important physics behind it? Okay, that's also something we can do it. Okay. So let me just show you one of the results first. The first, if we just use standard SED, that's a confusing matrix. The color line means something we predict. The row line means something in reality. Okay, you see most of them are in diagonal, right? So that means we could have very high precision and recall. The precision means the percentage of the diagonal turn along this column. The recall means the percentage of the diagonal turn in terms in this row. Okay, that means how much percentage of atoms, of not atoms, stars are predicted correctly. Because a star can predict with very good, more than 99%. And galaxy is also good, YSO is good, but less than 90%. Okay, but we feel we can do it better. So how about if we include error? I have to remind you that error bar is nothing to do with the nature. In principle, should be nothing to do with the nature of these stars, right? So this related to your machine or your observatory. However, we show that even if you include errors, it could also help us to identify that. The reason is that this error bar also including the information of flux, because the error bar, when intensity is larger, the error bar also larger. That's the textbook equation in statistical mechanics. So when we include that, we can see that both precision and recall are very, very high. So basically, we are almost recover the previous results. And so the first lesson we know is that these results nothing to do with previous theory. We just assume that we know the result, but we don't know how to explain it. We didn't tell them how to explain it, but he learned it. Okay, and he also learned how to distinguish galaxy and white smoke. Okay. And also, we find the observation error is important, as I said. And also, what we did, I didn't show is that because there are some deviation, right? In the test data, there's some deviation. We go to look at this case, okay, in details, and we identify them by updating new data by other observatory or papers to see if anyone can identify better observation. And what we find is that for this difference, for these diagonal terms, our results is more consistent with the recent observation. In other words, our model is trained based on previous theory, but the previous theory is not evidence. It's not ground truth. It's just theory. So it may fail too. So then we can compare. Although I learned it from their theory, but there are some difference, right? There are some objects which AI and previous theory predict differently. Then we check by another new data to see if this one is really YSO or galaxy. Then the answer is that most of the time, our AI is better or predict more correctly than previous theory, even though the previous theory is how we learn. So that means that in Chinese it means 听出于蓝. Yeah. Even if AI learned the previous theory, but the final effect, the final result is even better than that. In other words, because the reason that the theory, previous theory, is not true evidence. It's not true ground truth. So we catch something more important, not including previous theory. Okay, that's one thing. I hope you know that AI is not just to simulate something existing now. We also could provide something new. The second thing is that if we use normalized SED, we could also have pretty good, of course less, because you normalize it, so you have less information, right? So we find that we still have 80% percentage. It means what? It means that when you look at these structures, although these are almost distinguishable for human eyes, right? But AI can distinguish these two at least 80%. So I think this means what? That means that even after normalizations, AI can still tell what's the important structure, because this structure tells us physics, right? It tells us what's the major difference between the structure of galaxy and a YSO. So I think that's very exciting. That means that, okay, maybe we could have a better theory to understand this, not just a previous theory, which may be more complicated, but not accurate enough. Okay, finally, most surprising thing is that, how about if we just provide partial SD? The partial SD coming from the 3 bands, the data from the 3 bands in the longest wavelengths. In other words, previously we used 8 bands, 8 wavelengths, but now we just use 3. More precisely, we use 8 bands or 8 errors in these 8 bands, so that's 16 features. But here we just use 3 features only. We could all have pretty nice results, right? Then these results cannot be obtained if we use data in the shorter wavelengths. So that means longer wavelengths seems more important. But this is something they feel surprised because, as I said, the data, the errors, okay, when you do the measurement, it's always larger error bars in the longer wavelengths. So usually you don't believe that data much. But now my result is to tell you that if you just choose the 3 data from here, I can predict almost the same as your previous results with whole spectrum. So that kind of surprise, right? So it tells you that there should be something more important to detect, or maybe maybe I should say it this way. If you want to classify the data in the longer wavelengths, is certainly much more important than in short wavelengths, even though the data itself may have additional error bars. Okay. So why so? So the reason is not surprising because okay, let me finish this. If I just need three band information, I can plot the 3D plots like this. So the red one is star, the green one is galaxy, yellow, blue one is white. So you can see that in this three-dimensional space, these three types of objects are pretty well separated. Right? But if you plot it in 4 or 5 or 8 dimension, no one can see it by human eye. But now we can imagine how it is possible. So it helped the theory to build on a better understanding about what really happened, what's the mechanism of their lives, okay, to have these results. So therefore, you can also plot it in a different way. Maybe I skip this. Okay, that's good. So this what is means. This is also the result from the 3 bands. But this color is not observation data. This color is given by we just cut every directions into say 100 points, right? So in this 3D space, we have 100 times 100 times 100. It's about million number of points. For each point, of course, it is not a true star, but for each point, we can put into our model and then ask them to predict it should be star or galaxy. By doing so, we got an artificial boundary, okay, between YSO and the galaxy, and you can see how the boundary changed by you changing the wavelengths. So what this boundary means? This boundary does not mean that there are true stars around there. No, because stars just some points around, right? So maybe I can use this class to show it. These stars are our true data by observation. We have these stars, maybe this star, this galaxy, whatever. But for our models, if we put every point inside to make to ask them to make a prediction, we can figure out this boundary, right? So in other words, this boundary does not exist in the present data, but it is predicted by our model. So what this boundary means? This boundary means that if you have a good theory, if you want to build up an effective model, you should tell us this boundary. That's the equation we have, right? If you write an equation to tell that, for example, a criteria, if you want to, if this function above 5, it is star. If this function below 5, it is YSO. This function itself will give you this line. That's our theory. So this way of representation tells us if we can, our machine was trained by experimental data or trained by observation, right? But this observation is not the whole story. We get it from the whole observation data, but we can predict the boundary, okay, which tells the future theory to say that if we want to predict or develop a true model, and you should predict something similar to what I get here, right? Otherwise, you will not be consistent with experimental data. So that helps the future theory to develop future theories and to have a guideline to say if you want to develop a better theory, they should have this in mind, right? To say, oh, maybe at least he has to understand this. So I think that's something I hope to let you feel that it is possible for a machine to help a series to develop a better model to understand complicated systems. Okay, so that's the first part of my talk. Secondly, it is about the neuron science. In the neuron science, of course, it's further away from physics. Okay. Well, the questions we are asking the following. How can we define the polarity of neurons in the Drosophila brain? Drosophila is a kind of line. Okay. This database is from our school because our school has a very good brain science center that collect the largest database for the neuron image of the world, all over the world. Okay, so I think it's a true big data. So I talked to them, and maybe we can try to do something for you. Okay, so the problem is that can we define the polarity? The polarity means that the axon dendrite is where the signal coming or where the signal coming out. For example, this is the raw data, the image of a neuron inside the Drosophila. Okay, here is a cell, core of the cell. They call it soma. And this branch, this branch I know. Okay, this is the dendrite branch. This is the axon branch. So what it means is that the information was collected from here. There are many terminals around. When information coming through the soma and transported to axon, the axon will transport information or signal to another neurons. Okay, basically that's but the polarity means that very simple. If I give you an image, can you tell me this is dendrite, this is the axon, or this is the axon, this is dendrite? This is totally different, right? So this is a very fundamental problem. If you do not know which one is which, you cannot determine where the signal is going. Because all these neurons are connected to each other. It's not a simple connection, it's connected. One neuron can connect it with another dozens or hundreds of neurons outside. So if you don't know where the signal coming, right, so it's basically useless to have this image. Okay, but the situation, of course, they have some experience, okay, to know which. They could also do the experiments, okay, by using some chemical objects. Some chemical objects can attach to dendrite. Some of them attach to axon, so you can see. But it's too time consuming. But because we have more than thousands and hundreds and thousands neurons, so it's to take too much time. But if you want to look at it from the image, there's also a problem because you can see something like this. You know this is dendrite, you know this is an axon, but maybe they are just reversed, right? Because they look very similar. So not all neurons look like this. Okay, they can look at similar. Well, so now the problem is that how do we determine? This is not regular pattern recognition, because some people, when some previous researchers want to attack this problem, they look at it like a pattern recognition. Say, oh, the AI can do pattern recognition very good, but it's not, because we are not asking the AI to say that, oh, this is neuron, this is what. No, for this image, they have to identify which one is which. Okay, so it's not a trivial thing. Okay, and also there are many other, or maybe we should say, each neurons are different from each other. Okay, so there's no two neurons identical to each other. Okay, so therefore this problem is very difficult. Okay, so the first thing we need to do as a physicist, okay, I realized that why physics is very could be, or not, I should not say very helpful, but could be helpful to this subject is that we physicists usually think of something different. And then look at this image, but then we look at the effective model. So the first thing that I'm asking is that what's the effective model of this neuron? So this is so-called skeleton data, okay, because this is raw data looks too ugly. So they can make it to the skeleton with a line and a nose here. This color means the branch, the region of the brain. Okay, so you can forget it at this moment. So here, for example, this one is the dendrite, this one is the axon. So we make an effective model, which means that I mapped it onto these tree diagrams. The tree diagram means that each node, this node right here, but the distance from soma to this is soma. The soma to this node, I write a number here, for example. And so I normalize the distance. In a sense, is that every neuron, of course, every neuron looks differently in real space. Something larger, something smaller. Someone has many branches, someone has little branches. But all of them can map onto the same tree structures. Right? And again, of course, then I also have a rule saying that a longer branch I define it on the right, shorter branch I define on the left. So therefore, eventually I use this effective model to do the to determine its polarity. But of course, the situation is a little more complicated, I would say. So the first of all, according to their experience, they know the distance will be important factors. If you just put these nodes, okay, here's the axon, here's the dendrite, and just calculate its distance to soma, what's the path length to soma, you can have this distribution. In general, axon is a little bit farther away compared to dendrite in general. Or you can calculate the direct distance. Okay, you can also see something similar. But the accuracy is less than 80%. So maybe 80% is good for someone, but it's not good here because we have put so many neurons. So we should do it better. So that's the features we have used in our systems. Here I can list that some of them are important about the path to soma, okay, distance to soma. But there are also something related to the difference of length to next node, okay, and morphology. Well, when we say morphology, means that how it looks like. Some dendrite looks like more divergent than axons, for example, or the shape, the aspect ratio is different. So maybe I can use this slide to tell you that here, this is a dendrite, this is an axon. You can see they look different, right? But now the problem is that how do we teach AI to know these two are different? Because our machine has nothing that they don't visit it this way, right? We just put it into the space positions, but we need to calculate. For example, we could calculate the aspect ratio, and so these two look different. We can also calculate the curvature. When we say curvature, means that we can calculate the distance, the ratio between distance and the path length. Okay, so something like that. We can define this. So it's a little bit more complicated than what I said here, but it's a little bit too much detail. But anyway, if we can define it, but something we have to bear in mind, it is not 100% accurate. So in other words, there are many features, but none of these features is 100% important to determine the polarity. So each feature is important. So we have to include all of them together. So there's structures about this, so maybe I will skip it, but there are many steps, including to do data augmentation and to do reduce tree. But I think I had better skip that. And the first thing we also use XGBoost to do the classifications, and it can help us to know which features are more important. Okay, so then we also use so-called partial connected neural network because we find fully connected neural network may not be as efficient as what we want. So we also use some partially connected, which is some kind of like a CNN, okay, and make the output. And let me just show you the results first. So if we just do this, and there's a computation matrix, the prediction and from truth, and so we can have this. It basically tells us, oh, pretty good, very nice recall and precision. I have to tell you that previous method also provided by my colleague before. So previous method, they didn't use AI, they used another kind of machine learning, but well, I mean, it's not so efficient. The precision is always less than 90%. We have been about 85% already. But we don't feel very, satisfied, because if we look at these results, for example, here there's the axon as expected. Here is the dendrite as expected. But these nodes are predicted incorrectly. So we want to ask why this is predicted incorrectly. We find that because there's no correlation between this because when we do the prediction, it doesn't not know what the result for others. But maybe we can include in the correlations into this because correlation is an important physics, right? Important concept in physics. Then how do we include in correlations? Okay, what we did follow. We first to do the analysis. So here's the probability. Here's the number of nodes. So the axon. So here's the main one. The axon is like curve like this. Dendrite curve like this. This means that most of the axon dendrite are correctly predicted with very high probability. However, there are still something in the between, right? They are not correct. They are very confused. The probability to be axon or dendrite is roughly equal. Okay, so in these regions, we think that maybe we should give them the second chance. That just like a student, some students can pass easily with very high score. Some students you see basically no hope to pass. But there are something in between, right? Just above 60 and 70 or 50. Well, you think maybe you may make a mistake. So how you will do? Sometimes you will say this student we can do the exam again, right? To making sure that you are really qualified. But for other students, I think your destination has been finished. So then that's what we did. Is that we take out now the gray dots means what? The gray dot means that when we do the prediction, they are not fully supported by our machine. In other words, the probability is not very high. It's not fully 99% or 90%, or not fully just 10%. Okay, that's just in between. So that means it is very confusing to machine. These dots may be a little bit confusion for some reason. So we say, okay, if you're confused, we don't force you to make a decision. We just keep you like a gray dots. Then what I'm going to do? Well, we introduce correlations. The correlation means that, okay, if I know two nodes are axon, then maybe I should predict that it is also axon above. If we have two nodes to be dendrite, then the previous nodes should be also dendrite, right? But if there's something unknown, okay, so we can still predict it because this is unknown. This is dendrite, so we think this is dendrite. So by this way, and we also introduced the idea about mixed point, which means that if we have a dendrite and an axon, then it defines mixed point. But for each neuron, you usually will have only one mixed point or two mixed points. So this we don't need to worry too much about it. We also have to do the releveling from top down. So for example, if we have something like this, we define to be dendrite. Something like we define to be axon. So if we have both like this, we define it to be dendrite. Well, that's just a rule according to human experience. But I have to emphasize that this is what people have known in biology, but they don't know how to include it into the machine learning before. Okay, so then we find this a way we can do it. So we do it after machine do the prediction. So what's the outcome? The first thing is that this is the data I just showed, okay, without releveling. So there are some nodes which are not fully determined. So actually, it may be predicted incorrectly. But after doing this releveling, all of them are predicted correctly. So if you look at data, previous we have 95% pretty good, but after doing that, all of them are above 97%. Okay, so strongly enhanced. Okay, so after doing this, so in other words, we have included not only this distance. Distance, in fact, is known before, but we also including the curvature or say morphology, the structural behavior of this neuron, and also spatial correlations. So after including that, we have a very good result with accuracy more than 97% or even higher, that depends on parameters. So that will be good enough for us to go to the future. In the future, what we want to see that is part of the diagram part of the neuron we use. Okay, so if now we can almost identify all the probability of this neuron, and the next thing is that how do we determine they are connected or not? Once we know the connection and also the probability, we can finally determine how the signal flow inside the brain. So therefore, whenever you for example, when you see something for light, then we know how the signal is coming from the eye. Okay, when signal coming, we know where it go, and to determine what he wants to do next. Okay, that's how we can learn the whole function of the brain in the future. So the outlook or summary is that we believe that machine learning is a very powerful method, not only to simulate known data or known theory. If that's the case, it's probably not very interesting. But we believe that it could also generate new knowledge. The reason is the following. Usually, we may have unstructured experiment data that we don't know what the fundamental physics behind. We could also have just partially known theory, not fully known theory. In previous research, each of them are useless because we don't know how to connect it. But now if we have AI or machine learning to learn, then probably we could use this to get a little bit more understanding about that. So I think this is probably a way to apply machine learning or artificial intelligence to fundamental sciences. I hope this could be an example that you can appreciate. Okay, thank you very much.
Questions? Comments? Is it possible to use machine learning to look for the alien?
Look for what?
Alien. Yeah, something we don't know. Yeah. Are you looking for something we know?
Well, machine learning is not God. You know? So, but I think it can help to specify or to identify unconventional signal. So that's something we can learn because it has been applied, for example, in the TSMC. Right? So the whole process, the production process, it's very important to find out the strange signal, right? Because this means something maybe some signal are usual, but some signal are unusual, right? So these things can be trained. So in some sense, if you want to find a line, but maybe one way that you look at the signal from astronomy, and you actually to learn what is normal things. So maybe at one time that they could observe something unconventional, then they could remind you that, or maybe this one you should take a look at it. Okay, maybe that could help. So I think could be a way to predict earthquake. I think that should be possible, but I didn't do that. But I think in principle, because when you have an earthquake, you have the ground truth. So you can use that to learn from the previous data and to learn what really happened before that. At this moment, there are many theories, right, to do that, but none of this theory works. But AI don't need theory; they just need data. If you have ground truth, because when you have earthquake, it's ground truth. Right? But you can learn what happened before, maybe a month ago or even 1 day ago. What's the difference from the vibrations? What's the unconventional signal? We don't know, but maybe the machine can learn it, right? So I think that can be what we can apply. Any questions? Questions?
So I noticed that in the first part of your talk, DNA.
Yeah.
But it looks to me that the input data.
There is little.
So why do you use DNA?
Okay. We don't have to use CNN. We can also use standard deep neural network without convolutions. Well, in somehow my student, if we include that, it helps. So one of the reasons is that when we look at the spectrums, they are also correlated to each other. When you look at this point, it's better to know his previous information. So we find it help, but I will not say it's necessary. Okay, so but well, that's what we choose. But yeah, okay, you don't have to. But of course, maybe the percentage will be a little bit lower. But the final result is yeah, it's not necessary. And that's also something I observed that because the feature for fundamental science, the feature may not be as much as what people use in the industry, right? Because for the image, you may have millions of features. But for fundamental science, usually we just take important features, a few of them. But at least from our experience, we find that even for this kind of things, because if we have only 2 or 3 features, it's very simple, we can control it. But if we have millions of features, then of course we use CNN. But usually we have something in between. But I just want to show that it is still possible to do this analysis.
I'm curious when you say that the neural network is in the first part. The neural network is able to do better than conventional model. I wonder when doing this comparison, what is the third ground truth?
Okay, so because the data was collected about 10 years ago. Okay, or maybe say the data was identified about 10 years ago by previous theoretical group. Okay, in Maryland, okay, there's a huge astronomical group. They also observed YSO. They developed some theory. They want to classify which one is which. Okay, so they have results already. But for example, they probably predict, okay, this the thousand of stars are young YSO. But no new data, not everyone will look at it individually, right? Or that's what you say, oh, maybe it's true. But if nothing related to my research, I will not check for you, right? But some of them has been checked by new data, by new observation. Okay, they got other information, not just these 8 things. They got other information. And some of them has been identified in the catalog, saying, oh, this is the YSO or it is not. So, but when we do the comparison, we compare with previous data, you know. So there are some difference. When we look at this difference, we look at the third one. But the third one is the more advanced, right? So this it might be better.
Right.
Okay, so that's fine.
Other questions, comments? So if not, let's go on to yes. Oh, sorry.
I have a question about the Drosophila part of your talk. So, are you analyzing the data from that Drosophila brain, or are you analyzing real-time Drosophila brain? Because it could be a huge difference.
You mean the measure in real time? What do you mean real time?
The real time means that the Drosophila brains, the Drosophila are still alive, and you can observe how the signal flows.
No, I have to say, we didn't measure signal flow. Okay, we just identify which direction it will flow.
Right.
But all the Drosophila, of course, are dead. They couldn't take this image. Okay, but so they have to take thousands and thousands to average the image in order to identify this neuron. So each image is an average of maybe 100 dead, very poor Drosophila. So they identified it. But the important is that which direction the signal flow, right? Even if you have an image, this will be the same, no matter the flights, alive or dead. But so they have their goal is to reconstruct the whole brain. So for Drosophila, there are about 140,000 neurons about that. But they have about more than 70,000 already. More than half, more than 50%. So the Professor Zhang, the Zhang Anshi, he believed that maybe they could finish this in 5 years. So that they have a completed database of a real animal, not trivial animal, not a cell, non-trivial animal, they know which neuron is which and how they are connected. That's their goal. But even you have this goal, but you still need to know how the signal goes, right? So that's how we can help.
It's time to start. Let's thank the Dao again and thank all the speakers.
You are free to leave. So welcome, sorry to say, happy mid-autumn. Okay. Sorry, we don't have a bouquet. Maybe we should prepare.